In this presentation, we focus on a deceptively simple question with huge operational consequences. In a container terminal, what is the best sequence for a single crane to lift containers so that the entire bay is cleared as fast as possible? Our objective is to minimize the total completion time, also called the make span, while strictly respecting operational constraints such as feasible dual lifts, safety limits, and stacking realities. Modern container terminals operate like tightly coupled systems. Thousands of container moves, limited crane capacity, strict vessel schedules, and high labor and equipment costs all interact. When a single crane sequence is inefficient, the delay does not stay local. It propagates to the quay, the yard, the gate, and ultimately the wider supply chain. So we are not looking for a nice sequence. We are looking for a decision policy that reliably reduces time and risk. Imagine peak hours at a large hub such as the Port of Rotterdam. We have 24 containers arranged in a 6x4 grid, stacked up to 3 levels. One overhead crane must clear the bay. Importantly, this crane can operate in 2 modes: single spreader, lifting 1 container at a time, and dual spreader, lifting 2 simultaneously. Every step requires 2 linked decisions: which container or which pair of containers to lift next and which mode to use. Containers are heterogeneous. They differ in weight, destination, priority, physical position, and time pressure. These differences create real constraints and hidden dependencies. Some pairs cannot be lifted together in dual mode. Some containers are urgent and should not be delayed. And in stacked configurations, accessibility can depend on what has already been removed. In practice, choosing the next lift is a constrained, multi-criteria optimization problem. The crane operator is constantly balancing multiple objectives, selecting the next container, deciding single versus dual mode, minimizing travel distance, respecting safety and stacking constraints, and honoring priority. And these decisions are not independent. A choice that looks good right now can create a costly position and mode situation 2 moves later. That's why we frame this as sequential decision-making, optimizing the entire trajectory, not one step at a time. Poor sequencing means extra time, extra moves, and extra congestion. Even small inefficiencies compound quickly. Vessel delays can cost thousands of dollars per hour. Downstream schedules get disrupted, gate operations become congested, and service-level commitments are missed. In short, sequencing quality directly affects terminal throughput and competitiveness. Optimization is not a luxury here, it's a requirement. This problem explodes combinatorially. For 24 containers, the number of possible lift sequences is 24 factorial, an astronomically large search space. And that is before we even account for the mode decision at each step. Brute force evaluation is impossible. That's why we need a tiered toolkit, exact methods for small cases, and smart approximations for realistic sizes. We will solve this problem through 4 tiers. Tier 1 builds a complete mathematical foundation using dynamic programming for optimal solutions on smaller instances. Tier 2 introduces classic, fast heuristics that can run in real time. Tier 3 uses advanced meta-heuristics, specifically genetic algorithms to search globally without enumerating everything. Tier 4 augments the process with reinforcement learning, aiming to learn high-quality policies from experience. In Tier 1, we leverage a key property. The problem has optimal substructure, meaning an optimal solution can be constructed from optimal subsolutions. This makes it suitable for dynamic programming. Here, completeness matters. We explicitly define sets, parameters, state variables, decision variables, the full objective, constraints, and the dynamic programming recurrence. This tier serves as our correctness baseline and a benchmark for the other approaches. We begin by defining the sets that structure the problem. C is the set of containers to be lifted. P is the set of crane positions. M is the set of operating modes, single and dual. These sets allow us to represent both movement decisions and mode decisions in a unified formulation. The goal is clarity. Every index in the model must correspond to something physically meaningful in the terminal. Next, we specify parameters, inputs that describe the instance. For each container, we know its weight and its position in the bay. Movement times also depend on the operating mode, so we distinguish travel time in single mode versus travel time in dual mode. These are not abstract numbers. They can be measured from crane telemetry or calibrated via simulation. Accurate parameters are what make the model operationally credible. The second parameter set captures handling and switching. Handling time per lift differs by mode. Handling time in single mode versus handling time in dual mode. And if we switch modes, we pay a setup time. This immediately explains a common misconception. Dual mode is not automatically better. Dual can increase throughput, but it may also carry higher handling time or switching overhead, so the model must trade these effects explicitly. Dynamic programming is only as good as its state definition. We define the state as the dynamic programming value for S, P, and M. Here, S is the subset of containers already lifted, P is the current crane position, and M is the current operating mode. This state is intentionally compact. It summarizes exactly what we need to evaluate future decisions without storing the entire history. Let's interpret the state intuitively. S tells us what remains to be done. P determines the travel cost to the next candidate container. M determines whether switching costs apply. As S grows, the number of possible subsets grows exponentially, which explains why dynamic programming does not scale to large N. Still, for small and medium cases, dynamic programming is the gold standard because it provides an optimality guarantee. Now we formalize what the decision looks like. We use one variable to indicate whether the crane moves from position I to position J using a chosen mode. We use another variable to indicate whether container I is lifted using single mode or dual mode. And we use a separate indicator variable for whether a mode change occurs at a given step. These variables allow us to write the total time as the sum of travel, handling, and switching components. Our objective is to minimize total completion time. The first term aggregates movement time across transitions and modes. The second term sums handling time, which depends on whether lifts are performed in single or dual mode. The third term adds penalties for switching modes. The result is a realistic objective that captures the true cost drivers of crane operations. It helps to think of the objective in three parts. Travel time shapes the route the crane takes through the bay. Handling time captures the lift execution cost and differs by mode. Switching cost discourages unnecessary oscillation between single and dual. Good solutions typically exploit dual opportunities strategically, but avoid excessive switching and avoid long, empty crane movements. The first constraint ensures completeness. Every container must be lifted exactly once. No container can be skipped, and no container should be lifted twice. In dynamic programming terms, this is enforced through correct transitions of the lifted set S, but it is essential to state it explicitly as a hard feasibility requirement. Dual mode has a capacity limit. At most, 2 containers can be lifted in a dual spreader operation. This is the equipment constraint written mathematically. In practice, the dual decision is also constrained by weight limits and geometry, but this constraint captures the fundamental capacity ceiling. Not every pair is compatible for a dual lift. Containers can be incompatible due to weight, size, position, or safety rules. This constraint prevents selecting incompatible pairs in dual mode. It ensures that the mathematical solution is executable in real operations, not merely optimal on paper. This recurrence is the core of the dynamic programming model. From a given state, again, the dynamic programming value for S, P, and M, we consider lifting a container that is not yet in S. Choose a mode, pay travel time from the current crane position to that container's position, pay handling time for the chosen mode, and if we changed mode, we also pay the setup cost. Then we move to the next state where that container is added into the lifted set, and the crane's position and mode are updated. Dynamic programming chooses the minimum cost continuation, capturing long horizon optimality. To make the model concrete, we use a small 6-container instance. We specify positions in a simplified grid, container weights, handling times for single and dual modes, a dual weight limit, a setup time for switching, and a travel time function based on distance. This kind of example is perfect for understanding dynamic programming mechanics because the state space is still manageable and the optimal path can be traced. This figure visualizes the Bay geometry and the dynamic programming-derived optimal clearing pattern. The key insight is that the best sequence is not always pick the nearest container. Sometimes you travel slightly further to create a high-value dual opportunity, and that reduces the total make span. The image helps connect the math to physical crane motion. Dynamic programming starts with the base case. No containers lifted, zero cost. Then it builds optimal values for progressively larger subsets. For example, states where one container has been lifted, then two containers, and so on, always storing the best next action for each state. Once the full set is reached, we can reconstruct the optimal sequence by backtracking through these stored decisions. For the sample instance, dynamic programming identifies a sequence that interleaves dual and single lifts in a way that minimizes total time, yielding a make span of 18.7 minutes. The purpose of this result is not only to solve the small case, but to provide a trustworthy benchmark. When we evaluate heuristics, genetic algorithms, or reinforcement learning, we need a reference point that represents true optimal performance. The limitation of dynamic programming is computational scaling. The number of possible lifted sets grows exponentially with the number of containers, which quickly becomes infeasible as the problem gets larger. That is why in real terminals, dynamic programming is used for small instances, training, validation, and benchmarking. For large bays or real-time decisions, we need faster approximations, leading us to Tier 2 and Tier 3. Tier 2 is about speed and reliability. We use a constructive heuristic inspired by weighted shortest processing time, adapted to crane movement and mode decisions. The heuristic assigns a priority score to candidates, selects the best available next move, and checks whether a dual lift is feasible. It does not guarantee optimality, but it produces reasonable sequences quickly enough for operational use. Read this flowchart as a loop of scoring, selecting, feasibility checking, executing, and updating. At each iteration, containers are evaluated using a priority function. This method is based on weighted shortest processing time. If a dual lift is possible, the heuristic tries to pair containers to improve throughput. Then the system state is updated, and the process repeats until all containers are lifted. The logic can be summarized as high urgency at low cost first. A typical score might look like priority divided by a combination of weight and travel distance. Once a candidate is selected, we attempt to find a compatible partner for a dual lift, subject to weight and safety constraints. This creates a practical balance: meet priorities, reduce travel, and exploit dual capacity when it truly pays off. In other words, it is a weighted shortest processing time rule adapted to crane operations. In this code section, you typically see the core data structures, container attributes, scoring functions, and the candidate selection loop. A crucial detail is that scores should be recomputed as the state changes, because after each lift, accessibility and pairing opportunities can change. That's why the heuristic behaves dynamically, not as a one-time sorting. This continuation handles feasibility checks and state updates, validating dual compatibility, enforcing weight limits, updating the crane position and mode, and accumulating total time. The major trade-off is clear. This approach is deployable and fast, but it can miss globally optimal sequences because it makes decisions myopically. Here we see an illustrative run. Each lift is listed with its type, selected containers, position, and time. This format is valuable in practice because it is easy to audit and explain to operators. The total time is 55.3 minutes in the example. The goal at Tier 2 is not perfection, it is consistent, understandable improvement under tight time constraints. The heuristic is computationally efficient, often described as roughly cubic time in the number of containers. In practice, it can handle large instances quickly. Quality is typically within about 15 to 25% of optimal, which is often acceptable for real-time decision-making. And importantly, heuristic outputs can serve as good initial solutions for meta-heuristics in Tier 3. Tier 3 changes the strategy. Instead of constructing a single solution greedily, we evolve a population of candidate solutions. A genetic algorithm uses selection, crossover, and mutation to explore the search space globally and escape local optima. This is especially powerful for medium-sized problems where dynamic programming is too slow, but high-quality solutions are still required. This figure shows the evolutionary cycle. Start with an initial population, possibly random or seeded from the heuristic. Evaluate fitness, select the best candidates, produce offspring via crossover, apply mutation to maintain diversity, and iterate. Over generations, the best solution improves, and the population converges toward high-quality sequences. The chromosome encodes a full plan. In this problem, we use a two-part encoding, a permutation representing the container lift order, and a binary string representing mode decisions, single versus dual for each step. This representation is powerful because it optimizes both the sequence and the operating mode decisions together. The operators are what make the genetic algorithm work. Tournament selection favors good solutions without losing all diversity. Order crossover combines parents while preserving valid permutations. Mutation, like swapping two containers or flipping a mode bit, injects exploration and prevents premature convergence. The key is to generate new candidates that remain feasible and meaningful. In this first code section, you typically see the chromosome structure, initialization logic, and the fitness function. The fitness function must reflect the real objective, total time, while also incorporating penalties for any constraint violations. Without a well-designed fitness function, the genetic algorithm will optimize the wrong thing, so this is the most important modeling decision in Tier 3. This continuation contains the evolutionary loop: selection, crossover, mutation, elitism, and generation updates. Elitism ensures that the best solutions are not lost. Stopping criteria, such as a maximum number of generations or no improvement over time, control computational budget. Together, these mechanisms determine how the genetic algorithm searches and how reliably it converges. Genetic algorithm performance depends strongly on hyperparameters: population size controls exploration capacity, crossover rate controls recombination, mutation rate controls diversity, and elite size controls stability. Too little mutation can lead to premature convergence. Too much mutation can turn search into noise. In practice, parameter choices should match problem size and the available computation time. The convergence table illustrates steady improvement over generations, for example, reducing the best time from 58.3 minutes to 41.7 minutes by generation 100. This matters because it demonstrates meaningful global search. Thousands of candidate solutions are explored, and the algorithm discovers sequences that a simple greedy heuristic is unlikely to find. Genetic algorithms are well suited to discrete, constrained optimization. They do not require gradients, they can be parallelized, and they can incorporate complex constraints through penalty methods or feasibility checks. In the example, the genetic algorithm improves upon the WSPT heuristic by 12.3%. That makes Tier 3 a strong compromise, significantly better solutions than heuristics without the infeasible cost of exact dynamic programming. Tier 4 focuses on learning a policy rather than solving a single instance. A reinforcement learning agent interacts with a simulated terminal environment, chooses actions, receives rewards, and gradually learns how to minimize total completion time while respecting constraints. This is particularly valuable when similar problems repeat over time and the environment is dynamic. This diagram shows the agent environment loop. The agent observes the current state, remaining containers, crane position, mode, and time context, then selects an action such as a single lift, a dual lift, or waiting. The environment transitions to a new state and returns a reward. Through repeated episodes, the agent learns which choices lead to the best long-term outcomes. To make reinforcement learning rigorous, we model the problem as a Markov decision process. The state at time ti captures what matters now. The set of remaining containers, crane position, current mode, current time, and sometimes recent history. The action space includes single lifts, feasible dual lifts, and optional weighting. This formalization is what allows learning algorithms like deep queue networks to be applied. The reward function defines what the agent learns. We typically start with negative time increments. Slower actions yield worse rewards, and then add penalties for constraint violations and for deprioritizing urgent containers. Reward design is the most delicate part of reinforcement learning. If the reward is misspecified, the agent will learn unintended behaviors. In a deep queue network, a neural network approximates the queue value of each action, the expected long-term reward if we take that action now, and behave optimally afterward. Inputs can include container status vectors, normalized crane position, mode encoding, and time and distance features. Overtraining, the agent shifts from greedy short-term decisions to strategies that optimize the full sequence. In the first part of the implementation, you typically define the environment dynamics, state representation, and the queue network architecture. One critical practical detail is action validity. Infeasible actions, like incompatible dual lifts or inaccessible containers, must be masked or penalized properly, otherwise the agent wastes learning capacity exploring impossible behaviors. The second part covers the training loop, selecting actions, computing rewards, storing transitions in a replay buffer, and updating the network using mini-batches. Stabilization techniques like a target network and experience replay are essential. Without them, learning becomes unstable and performance can fluctuate. Think of training as repeated practice. The agent clears many bays across many episodes. Early on, it explores. Later, it exploits what it has learned. The replay buffer improves sample efficiency, and epsilon greedy exploration ensures that the agent continues to discover better strategies. With enough diverse training scenarios, the learned policy can generalize beyond the exact cases it has seen.